Okay? Okay, ladies and gentlemen? You still awake? Not fainted yet, yeah? Okay, now, so this one is the final version. Right? So, in the x direction, your momentum conservation becomes this. Basically, this one is the one that we are using later on. That's all. I just want to show you how we got this from the scratch. Okay, clear? Huh? You can ask me how to derive it if you want. All good, yeah? Okay, now if you do the same for y and z direction, you will have exactly the same. You see? Exactly the same, just different in the component. You can see the difference. This one has u, this one has v, w. So after few times writing it, you will just realize it's very simple. Just change u, v, w. The next one you can see sigma xx, right? It moves to the middle, yy. So it's like a matrix. Not those matrix, right? Not those movie matrix. It's matrix mathematics. See, it's moved from here to there, right? And the tau, when you are walking in the x direction, the plane is in the rear part. This one is the direction, and this one is the plane. Which means when you are talking about, let's say, this one, your x is. How do you want to have your x? There. Okay, that is your x. So this one is the plane normal to the x. This is the plane x, we call it. The shear working on that direction is tau. What do you want to call that direction? Y. Okay, so shear on that direction is called tau y working on the x plane. Oh. So if you have this is plane Z. If we are looking at that, Y, so it is tau Y Z. Excellent. Right? You know now, right? All about it. Okay, now if you look at this, it looks like one symbol only, but unfortunately, how easy it is still so-called a shear stress, not vector anyone, it is a shear stress tensor. Tensor is, if you have u, you will have ux, y, but we are talking about which has something like that. This is vector, this is tensor. Okay, so even though it looks like only like this, at the end of the day, it can be complicated. However, for our course, of course, we want to make our life simple. Right? So this is how the normal stress looks like, and this is how the shear stress looks like. This is the simplest that we can get for you. can still see that u dx, dv dy, and so on. And this is only valid for this. Only for isotropic Newtonian fluid. What isotropic mean is the properties on all direction is the same. Is there any material that has different properties on different direction? A lot. A lot of material is actually non-isotropic. But fortunately, our lovely water is isotropic Newtonian fluid. Okay? It will be totally different when you are working with Shell, Halliburton, Petronas, and so on. Those things that give you a lot of money. Right? Because they give you a lot of money, of course they will give you a lot of good. So in real life, you may not find this one. Okay, but in our course, you will find this. Okay, so this one is only valid for Newtonian fluid isotropic. Okay, and you plug in those, you put this into here. You see, this one is still sigma zz, right? So you do not want to have that sigma zz. You put sigma zz is equal to minus p plus 2 mu dw dz. So you plug in this to that, you will end up having this one. Okay? Okay? So you do some mathematical manipulation, you will end up having this. Okay? Similarly for the y and z direction. Right? And the good thing is, if you deal with incompressible fluid, if you deal with it, I hope you still remember, for incompressible fluid, du over dx plus dv over dy plus dw over dz is equal to 0. Good thing to know. Okay, so this one will cancel. Okay, this one will be cancelled out. So you end up having this, a much simpler equation that commonly called as a Navier Stokes equation. So this is the Navier Stokes equation. Even though it looks simple until today, if I'm not mistaken, correct me if I'm wrong, there is no exact solution for Navier Stokes equation. Okay? The only way you can solve it is taking a lot of simplification or take a numerical approach using computational fluid dynamics. That's the only way you can solve it. Right? In this course, actually I want to introduce both, but for the next one, in the next half an hour, we will show you that for a very specific cases, we can cancel more of this, and we will have a much simpler equation that you will love, hopefully. Okay, so this is the so-called Navier Stokes equation, and you know where it comes from now. Any question? Okay, if you want to convert that, okay, I don't like this one. This one looks too complicated. Okay. If you remember on Tuesday, I introduced you to the so-called del operator, right? So if you are using those del operator, you will have this simple equation. So this simple equation, if you expand it, it becomes this one. But if you want to make it simple, okay. So it has 4 variable unknowns. U, see, U is part of this. U v w is the component of velocity. Pressure is from here. Okay, so you have 4 components, 4 parameters, and 4 equations. Because this equation is three equations. It is not one. It has three components, x, y, z. So you have four equations, four parameters, which means it is a well-posed equation. A well-posed equation means you can solve it. If you remember your simultaneous equation, you have a plus bx equal to 2, right? And then you have c plus dx equal to something. You can do a substitution or elimination to get the value of x and y. Same goes for this one. Okay? So you have four equations, four parameters, or four unknowns, then it is well posed, you can solve it. Okay? So if you want to take a simplification further, you thought that the flow is inviscid. You remember inviscid flow? Inviscid flow is where the viscous effect is negligible, right? When you do that, of course, the viscosity becomes zero. Then you end up having only this, and this one is called Euler equation. Okay? Still not familiar with you, but if you remember, if you take inviscid steady state, this one will go on, right? Inviscid steady state, these two will give you this gone. This will give you your lovely Bernoulli equation. So basically, Bernoulli equation can be derived from the Navier Stokes equation after all of those simplifications. Okay?